A machine just looked at a piece of rock and refused to believe a human made it. No theory, no guesswork, just measurements. And the numbers it produced are the reason this video exists. You're going to see evidence that doesn't fit neatly into any history textbook, and a twist near the end that even seasoned researchers didn't expect not far from the Nile. In southern Egypt, there's a quarry that most tourists rush past on their way to the temples. It looks like nothing special. Cracked stone, half-finished blocks, sand, silence. But get close enough, and something about the surface starts to feel wrong. Not damaged, not random, deliberate. That feeling is exactly what sent a team of researchers down a rabbit hole, one that ended with an AI system staring at thousands of measurements and producing a number nobody expected. Let's start with the material itself, granite. This isn't soft sandstone you can scratch with a fingernail. Granite sits near the top of the hardness scale, tougher in many ways than the steel tools people assume were used to shape it. Now, look at what's carved into it. Long, sweeping grooves that curve like waves, spaced almost identically apart. No jagged stops, no uneven gouges, just rhythm, repeating across meters of solid rock. Most people who see it for the first time ask the same question. Are you sure this is thousands of years old? Because it doesn't look like ancient work. It looks engineered. For decades, the accepted story has been simple. Ancient workers used handheld stones, specifically a hard rock called diorite, and pounded the granite again and again until it slowly gave way. Historians estimate tens of thousands of laborers worked these quarries in rotating shifts, hammering for hours at a time, for months, sometimes years, just to free a single block. It's a story about scale, brute force multiplied by manpower. On paper, it works. But someone eventually decided to actually test it. A team built real diorite hammers. They brought in skilled workers. They struck real granite thousands of times, exactly the way the old theory describes. The result wasn't pretty. Some strikes left deep gouges, others barely scratched the surface. Edges cracked unevenly. Spacing was inconsistent. Exactly what you'd expect from human hands, tired, imprecise, naturally variable. Now compare that to the real marks in the quarry. Smooth, evenly spaced, almost identical from one groove to the next. The experiment was supposed to confirm the old theory. Instead, it quietly broke it. Eventually, researchers stopped relying on opinions and started relying on data. Engineers created ultra-detailed 3D scans of the quarry surface, a technique that stitches together thousands of photographs into a precise digital model. That model was then fed into an AI system trained to analyze tool marks without telling it anything about where the data came from or what era it belonged to. The AI's only job: measure everything. Curve radius, entry angle, depth, spacing, consistency. It analyzed more than 800 separate cuts, and the number it returned shocked the people who built it. Total variation across all those cuts, just over 4%. To understand why that matters, you need a comparison point. Even a master craftsman repeating the exact same hand motion will typically show somewhere between 12 and 20% variation. That's not a flaw, it's just being human. Hands get tired, grip shifts, angles drift slightly with fatigue. A 4% variation isn't very skilled human. It's something closer to a machine repeating the same motion on a loop. The entry angle told the same story, staying within about 2 degrees across hundreds of separate cuts scattered across different parts of the site. That's the moment this stopped being an archaeology question. It became an engineering question. So the AI did what it was built to do. It compared these marks against a database of tool signatures, ancient and modern. Hand hammers didn't match, too irregular. But 3 modern technologies did: diamond-tipped rotary cutters, high-pressure water jet systems, and ultrasonic cutting tools equipment that didn't exist before the 20th century. The closest match, with roughly 94% confidence, was an industrial rotary cutting process. Let that sit for a second. A measurement system found that ancient stone cuts most closely resembled tools that wouldn't be invented for thousands of years. Here's where it gets physically strange. Scattered through the quarry are narrow shafts, some plunging 30 to 50 feet down, barely 3 or 4 feet wide. If the hammer theory is correct, a worker needs at least 1.5 feet of swinging room to generate enough force to dent granite. Inside these shafts, that space simply doesn't exist. In some sections, a person can barely stand upright, and yet the same precise, curved cutting pattern continues all the way down the shaft walls, identical to the marks in the open quarry above. Something worked in a space too tight for a swinging arm. What that something was, nobody has fully explained. Zoom in far enough, and stone tells the truth. When granite is struck repeatedly repeatedly with a hammer, it fractures tiny cracks spreading outward and downward beneath the surface. Under a microscope, hammered granite looks chaotic, almost shattered. The Aswan cuts look nothing like that. Instead, researchers found something called a shear pattern, a clean, sharp boundary between the cut surface and untouched stone, as if something had sliced through rather than smashed through. Almost no fracturing beneath the surface at all. At extreme magnification, fine spiral grooves appeared, the kind of mark left by something spinning continuously in one direction. Tiny zones of heat damage showed up too, concentrated at single points, the signature of friction from a rotating contact, not a hammer strike. Researchers even found microscopic particles of corundum, a mineral almost as hard as diamond, still commonly used today in industrial cutting discs. None of this fits the hammer story. All of it fits something closer to a rotary cutting tool. Now here's the twist that turned this from a curiosity into a real debate. In several spots, ancient red ochre paintings sit on top of the cutting marks, meaning the cuts came first and the paintings were added much later. Some researchers estimate those paintings could predate Egypt's earliest known dynasty by roughly 2,000 years. If that's accurate, the cuts beneath them are even older. When the AI compared cut precision against estimated age across the entire site, it found something almost backwards. The oldest marks were the most precise. The newer ones got progressively rougher. Normally, technology improves over time. Here, the opposite trend showed up, and it held with extremely high statistical confidence, not just in one isolated spot, but across the whole dataset. There's one more piece of evidence that makes this even harder to dismiss. The largest obelisk ever attempted in ancient Egypt, still attached to its bedrock, abandoned mid-project. If finished, it would have weighed over 1,000 tons. The official explanation is a crack that formed during cutting, forcing workers to stop. Reasonable enough, except cutting marks continue beyond the crack, meaning work didn't stop the moment it appeared. It carried on for a while longer, and the precision of those final cuts, identical to everything else on the site. No drop in quality, even near the end. So why did a 1,000-ton project just stop, with no record of anyone ever returning to it? If this were limited to a single site, you could call it a coincidence and move on. But the same cutting signature shows up at the Giza pyramid complex, particularly around the Valley Temple, a structure where multi-ton granite blocks fit together so precisely that you can't slide a blade between them. When AI compared the marks from both locations, the difference was under 5%. Different stone, different site, nearly the same method. The same pattern, oldest cuts most refined, later cuts rougher, repeated again at other granite sites along the Nile Delta. This isn't a local mystery anymore, it's a regional one. So where does that leave us? A method capable of cutting hard granite with near mechanical precision. Evidence that the oldest examples were the most advanced, not the least, and a widely accepted explanation that breaks down the moment it's tested against the actual stone. Maybe there's a simple answer still waiting to be found. Maybe a piece of the historical record is genuinely missing. Either way, the granite isn't offering any explanations on its own, it's just sitting there, exactly as it was left, daring someone to figure it out. If a machine can find an anomaly this significant hiding in plain sight, you have to wonder what else has been overlooked. If this kept you curious until the very last second, subscribe and turn on notifications, because the next mystery we uncover might be even harder to explain.